Okay, guys, welcome back to another lesson. A little bit different than before, as you can see. My video, my face cam, I should say, is a little bit smaller. This has a lot to do with graphing, so I highly encourage you with this lesson. Make sure you have some graph paper handy. I did post some on Google Classroom, so that way you can always print that out if you'd like. But today's lesson and topic is going to be optimization with linear programming. So what does that whole thing mean? Well, it comes down to, I'm going to give us a function with two variables in it, let's say x and y. And I want to figure out what numbers I can plug into that function that give me the largest and the smallest value, okay? That's the optimization part of this lesson, okay? Now, we're not going to worry about word problems yet. That's going to come down the line. Today, I just want to know, can we work with these numbers and figure out max and min, okay? So here we go. Back then, we solved systems of linear inequalities by graphing. That was the previous lesson. Today, and this is part one, all right? We're gonna have part two later on, but part one is find the max and min of values of a function over a region. And then part two, which will be a different video, would just solve real-world optimization problems using linear programming, okay? So here's some vocabulary that we're going to talk about. The reason why it's called linear programming is, well, we're only dealing with linear functions, okay? We're not dealing with parabolas or anything like that, cubics, quartics. Okay, we're only dealing with linears functions, okay? So let's look at what feasible region is, okay? So on here, and I am going to try, let's see if I can do this. This is a new way of recording for me, and I'm going to see if I can get this. Oh, sorry, I can get this to work here. Maybe. There we go. Okay. So this little part I'm circling, this is called a bounded region because it makes a shape, specifically a triangle. We're going to be graphing three inequality statements, and they're going to create either a triangular region or an open-ended region. So a bounded region looks like this. And when we're done shading, we're going to see that all of these areas combined right here, okay, these guys right here are the solutions, or we could call them the possible solutions for a function, all right? And we're going to look specifically which one of those would be max or min. The max and min values are going to be the vertices here, okay? Those guys are going to give me those values, okay? Now, the other numbers that are in that area will work, but it's not going to give me the largest or smallest value. So this is bounded. An unbounded region right there, okay, is when it's not closed in. So you're only going to have two vertices to look at, but you're only going to have a max or a min. You're not going to have both, okay? A bounded region will, an unbounded region will not, okay? So let's take a look at an example here. Okay, so here's the first problem, okay? And here's the situation. Here's my function, okay? Now I'm not graphing this function, okay? I want to figure out what x and y values I can plug into there to get the largest or smallest number. But I have some restrictions. So what I'm going to circle here, these are the restrictions, okay? So for instance, I can't plug x values. I can only plug x values, I apologize. I can only plug in x values that are less than or equal to 5. I can only plug y values that are less than or equal to 4. And then to put another restriction onto there, I can only add these x and y values, and they can only be equal to 2 or bigger than 2. All right, so these are restrictions. I'll put R there for restrictions. I'm not going to spell it out because the mouse pad is hard to write. Okay, so if I follow these restrictions, I can then figure out what numbers I'm allowed to plug into this function. Okay, and that's the goal. So let's graph these to see what numbers satisfy all of those. Okay, so let me just clear this out. And we're going to go to Desmos here to do that. Okay, over here. So let's go ahead and graph the first one. So x is less than or equal to 5. We already know, and I'm actually going to get rid of my camera, so goodbye for right now. Okay. So I know that that's going to be a nice vertical line at 5, okay? And it already shaded it for us. You could do the shading afterwards if you'd like. Next, y is less than or equal to 4. Okay, that's a horizontal line, and we're shading beneath it. And the final problem, now notice, it's not written in slope-intercept form. Desmos will graph this no matter what you give them, but I would like for you to put it in slope-intercept form because you're going to be doing this by hand. So it's going to be, when I solve it, y is greater than or equal to negative x plus 2. Okay, so it's going to look like this. Now, when you're done graphing this, you're going to see a region of values. I'm going to slowly zoom out where all the shading intersects. So I'm going to plot these points here, 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 and here. Okay? So if you take a look, that triangular region contains all the possible numbers I'm allowed to plug into the function. Okay? Now, I don't want any just numbers to plug in. I want to find the numbers that'll give me the max or min. And that's going to be located at these critical points, which are also the vertices of these triangles, okay? Of this triangle, sorry. All righty. So I'm going to stop sharing the screen real quick so you can see me. Hey, how's it going? So what we're going to do, okay, right now, is we're going to write a table down and see which one of those vertices gives me the largest and smallest value of the function. So here are going to be the points. I'm going to list there. Now the function was 3x minus 2y. And then we're going to get our value here. What was our answer? Okay. So our points were negative 2, 4, 5, negative 3, and 5, 4. Okay. So I'm going to put that down. Critical points, okay, or vertices of the triangle. There we go. Okay. So let's plug these guys into here. So it's going to be 3 times negative 2 minus 2 times 4. I'm going to go ahead and just substitute the rest of them here. Next one, 3 times 5 minus 2 times negative 3. 3 times 5 minus 2 times 4. Now let's simplify each one. So for the first one, when I simplify, I get negative 14. This becomes 21. And this last one becomes a 7. Okay? Now looking at our output values, I could see that this guy right here gives me the largest output for this function. So this is going to be my max value. If I want the least or the minimum number that's going to be in this function, that's going to be this guy. So 5, negative 3 gives me the largest in this problem. Okay. Negative 2, 4 gives me the smallest number. Okay. Now, going back to that graph real quick. It looks like this. All right, it's a rough sketch. The other numbers that are in the shaded region are going to give me values, but they're not going to give me a value bigger than 21, and they're not going to give me a value that's less than negative 14. It's only by these critical points are we going to see those max and mins occur. Okay? Any questions? You guys are always so quiet, so I never know if you have questions. I know, cheesy joke, sorry. All right, so remember, that's the goal. I'm going to look at this function, okay, and I'm trying to figure out what x and y values I could put into it by these restrictions. And this area are all of the possible numbers I'm allowed to plug into this guy. But only the vertices, or those critical points, those guys are going to give me the max and min. So I have to plug those in to see which one it's going to be. Okay? Alrighty, let's try another one. So I'm going to share the screen again. Okay, so I'm going to delete everything here. Goodbye, so long, adios. Okay. Let's try this guy right here, okay? So looking at the problem, we have another function, all right? And then with that function, we have these restrictions. Let's see if I can get the drawing tool back up here again. Oops, so sorry. Oh, try again, hold on. No, I don't want to. I like how everything I want is not working. Here we go. Okay, I apologize here. So you can tell it's live because I'm not getting this right off the bat. I'm not editing it. So here's the function, and I want to figure out what numbers I could plug in for x and y that give me the largest and smallest value. However, these guys are the restrictions, okay? So as long as my x and y values follow these restrictions, I can then see which one of those I can plug into here that gives me that, okay? So here's what I'm going to do. Let's go back to Desmos here. And once again, and it's very critical that you know this, I am not plugging in the function. It's not being graphed, okay? Only the restrictions are graphed because that gives me the numbers I'm allowed to use, okay? And just like before, I'm going to make sure that I write these in slope-intercept form so I can graph it. Because the goal is you're not going to use Desmos to graph all these. You can use to check it, but I want to make sure you know how to do this by hand. So for the first one, okay, it's going to be, if I solve for y, it'd be y is less than or equal to, let's see, it's going to be negative a half x plus 1. Oops. X plus 1. There we go. That looks a little bit better there. Okay. So there's the first one graphed for us. Okay. Now we're going to go ahead and graph the next one. Well, actually, it's not going to be a negative. It's going to be a positive. There we go. Sorry about that. Okay, the second equation. If I solve for it, now notice y is negative, so it's going to change the sign. So it's going to be greater than or equal to. All right. And it's going to be another positive x, but it's going to be a half of a positive x, just like that. And it's going to be a, what, minus 2, I believe, for that guy. And then for the last one, okay, this guy right here, it's going to be y is greater than or equal to negative x minus 2, just like that. Okay. Now let's look at our graph. Notice this region right here, okay, this little, it's like a ray, like a spotlight in a way, is my region of values I'm allowed to put in my function, okay? Now notice I only have 2 critical points. This will be an unbounded region. So that's telling me I'm either gonna have a max or a min, not both, okay? Well, let's go ahead. So I'm gonna stop sharing. So we're gonna plug these 2 points in the function and see which one it gives me. All right, so let me just click the stop share button right here. Hey, I'm back. All right, and we're gonna point this down. Okay, the new graph, new table. So here's my points again. All right, so here's my function, which was what, 2x plus 3y. And then here is the answer, the value that it gives me. Okay. The 2 points in question were -2, 0, and the other one was 0, -2. So let's plug these in. So I'm going to go ahead and substitute these values. Okay. Now let's simplify. So the top part, this is gone. That just is -4. This is gone, so that just gives me -6. Okay. So as you can see, we don't have a maximum value here, right? Technically, we don't. We only have negative numbers. So there's a minimum value, but what is the overall, what is the least value in this problem? It's this guy right here, okay? So this is a minimum. So this is my minimum value. If I plug in 0 and -2 into this guy, I'm going to get the lowest number that this function can spit out, which is -6, okay? So once again, looking at that graph, like this, It was all these guys. Now, I'm not saying that these solutions can't be negative, but it's not going to go past -6, okay? I could still plug in other numbers in here. They're still allowed to be plugged into here. I'm not saying that at all. I'm only saying that these critical points, okay, that these guys right here are going to give me a max or min. So it's giving me the floor and ceiling of what this function can spit out, given we're within those restrictions that we just graphed. These are all those restrictions that I just graphed. Okay. Alrighty. And that's it. Okay. I do have another example. It's listed in my notes, so you can take a look at that. All right. And please do. Okay. Try it out. Solve it for yourself. But I wanted to give you one example of an unbounded and a bounded region, so that way you can make those comparisons. But this is just part 1. Now, my notes include part 2, which is the word problem aspect, and we'll do that later. For the word problems, we're going to come up with the function, we're going to come up with the restrictions, and we're going to graph it and figure out what the max and min is. What is the optimal values that we could put in this guy? And we're still doing bounded and unbounded regions in that section too. So, but that's it, guys. So I hope you're doing well. And until next time, all right, I'll see you guys in the next lesson. All right, take care, guys. Have a good day.